stationary points, maximum, minimum and points of inflection. To work out the coordinates for stationary points, differentiate and make your derivative equal to 0 because the gradient is 0 on a stationary point. So for example, if we have this function dy by dx, make that equal to 0, solve to get the y coordinates, substitute the x coordinates back into the equation of the curve, and then we have our coordinates for the stationary points. The function is said to be increasing where the gradient is greater than 0. For example, on this curve the gradient is positive here, and then we have a stationary point, and then the gradient's negative, and then we have another stationary point, and then once again the gradient is positive. So it's an increasing function here and here, and it's a decreasing function here, and we have stationary points here and here. Okay, so dy by dx, we make that greater than 0, we solve for our solution. So for x less than 0 and for x greater than 4, the function is increasing. So that's where the gradient is positive on your graph. For a decreasing function, the derivative is less than 0, it's negative. So dy by dx less than 0, and then we solve to get our solution. So between x equals 0 and x equals 4, the gradient will be negative. It's a decreasing function. Because we have stationary points at x equals 0 and x equals 4, it would be wrong to do this. In function notation, the solution looks like this. To work out the nature of the points, that means are the stationary points maximum, minimum or points of inflection, we have these conditions on the second derivative. So d2y by dx squared, so we're differentiating this, and then we substitute in our x coordinates for the stationary points into the second derivative. So when x equals 0, so if we put 0 in here, then our second derivative is equal to minus 12, and because it's negative, this condition is met, it's less than 0, so we have a maximum point for x equals 0. And then for x equals 4, so now we put 4 into the second derivative, substitute it in, so we have 12 this time, positive value, so our second derivative is greater than 0, so now we have a minimum point. So this stationary point is maximum, this one is minimum. The same solution in function notation. So the graph of our function here, because the coefficient of the cubic term is positive, we'll have this shape, and we have some stationary points, so the graph looks like this: 0, 30, stationary point maximum, 4 minus 2 here, minimum, and we have an increasing function for x less than 0, so this is x equals 0, this is an increasing function, positive gradient, and for x greater than 4, positive gradient. We have a negative gradient for x between 0 and 4, and the stationary points where the gradient is 0 here and here. Example 2, y equals x cubed, differentiate, make the derivative equal to 0 for stationary points, solve, substitute x equals 0 into the equation of the curve to get the y coordinate. So we have a single stationary point at the origin. For the nature of the point, second derivative, so differentiate the 3x squared, substitute in x equals 0 into the second derivative, we get 0, this condition. So our stationary point could be a maximum, a minimum, or a point of inflection. So we have to investigate by looking at the gradient of the graph on either side of our stationary point. So make a table with x values in the top row and then gradient underneath, and it's the sign of the gradient that we're after, not the actual value so much, just the sign, whether it's positive or negative. So when x equals 0, that's a stationary point. I already know the gradient is 0 there. If I take a point to the left of x equals 0, so x equals -1, then work out the gradient. So dy by dx, the gradient, is 3 times -1 squared, which gives 3, positive gradient. And if I take a value to the right of x equals 0, so x equals 1, so 3 times 1 squared will give me 3, that's a positive value. So I have a positive gradient, and then a gradient that's 0, and then another positive gradient. That's a point of inflection. So the other options that we could have seen would have been like this. So a negative gradient that's 0 and then negative again, a point of inflection. Positive gradient, 0 and then a negative gradient, maximum point. Negative gradient, 0 and then a positive gradient, minimum point. Example 3, y equals x minus 2 to the power of 4. So dy by dx, we make this equal to 0, and then when we solve we get x equals 2. Nature of the points, d2y by dx squared. Substitute in the x coordinate for the stationary point, and there's a single stationary point, x equals 2, we get 0. So we're back to this condition where we could have a maximum, a minimum, or a point of inflection as our stationary point. So as before, we take values of x on either side of our stationary point. So there's my stationary point. So if I take x equals 1 and x equals 3, values on either side, and we work out the sign of the gradient at each of these points. So x equals 2 is stationary, so that will be 0. When x equals 1, the gradient will be -4, that's negative. And when x equals 3, the gradient will be 4, that's positive. So we have a negative gradient, then a gradient that's 0, then positive, which means we have a minimum point. A minimum point at x equals 2.